Hi, in this short video we will discuss the effects of sucrose on energy expenditure and the respiratory quotient in the human body. This is because the current society is consuming more and more sugar without knowing the real biological effects of this intake. To study these effects, we designed an experiment, but first we will give you an idea of what we have measured. First we have the energy expenditure. This is the total energy cost of maintaining constant conditions in the body. Homeostasis. For our experiment, the respiratory quotient was an important aspect as well. The RQ is essentially the ratio of carbon dioxide eliminated to oxygen consumed. The formula for RQ is carbon dioxide eliminated divided by O2 consumed. An RQ closer to 1 typically means that carbohydrates is being burned, and a value closer to 0.7 typically means fat is being burned. Glucose requires less oxygen to be fully oxidized, and therefore the RQ value rises during glucose oxidation. The aim of the research was therefore to look at the difference in energy expenditure between two healthy young adults, of which one takes sucrose and one does not, while lying in a resting position having fasted for at least 12 hours. We hypothesized that the person who took the sucrose will eventually have a higher RQ due to the fact that after a meal, more carbs in the body will be used for oxidation, which results in a higher RQ. The person who did not take the sucrose but water instead will have a lower RQ because when fasting, more fat will be oxidized, which results in a lower RQ. The reasons behind these processes will be discussed simultaneously with the results. For this experiment, we used two healthy subjects. They were instructed to avoid strenuous exercise before the measurements. They were also asked to skip breakfast and remain fasted before the experiment to avoid external factors to influence the test results. The materials used were two indirect open-circuit calorimetry machines, producing the volume percentage carbon dioxide and oxygen from the room air and expired air, and the volume of expired air per minute. Sucrose was used as a form of dietary sugar to be taken in by P1, as much as 75 grams. Both subjects drank 250 milliliters of water. In one of the drinks, the sucrose was added. The subjects were laying down on two beds equipped with the calorimeter. They were in this resting position during 1.5 hours, of which a half hour was a baseline measurement, to measure the carbon dioxide and oxygen expenditure and composition of expired air. When the machine was done measuring, we looked at the RQ values and compared them with previous literature to answer our research question. We will discuss our results alongside the following paragraphs. In this first graph we can see the macronutrient oxidation in fasted state of P2. If we ignore the peaks, we get an average carbohydrate oxidation of 0.1 gram per minute. The formulas used for these calculations can be found at the end of this video. During fasted and rested state, the body naturally burns fat, because carbohydrates are not directly available as a source of energy. Protein oxidation is low, as expected, because this does not provide much energy and therefore is not an ideal energy source. The arrow indicates the moment of the intervention. However, the macronutrient oxidation did not really change after this intervention. You see the dotted line is the average carbohydrate oxidation if we ignore all the peaks. In this second graph we can see the macronutrient oxidation of P1, that is the person who drank the sucrose. Once again, the arrow indicates the moment of drinking the sucrose. You can see that a clear change in macronutrient oxidation, shifting from fat oxidation to carbohydrate oxidation. This can be explained by the fact that the person ingested a large amount of carbohydrates, which is now the preferred energy source in the human body. The other arrow indicates the protein oxidation, which again is very low. This graph shows the respiratory quotients of P1 and P2. The baseline measurement presented that P2 had a higher RQ than P1, which can be explained by different metabolisms between the persons. After the intervention, though, the RQ of P1 increased a lot, whereas the RQ of P2 stayed pretty much the same. You can see the blue line is P1, the red line is P2. So here we have the energy expenditure for both of the subjects. We don't see a visible change if you compare the placebo to the sucrose person. Therefore, we cannot see a sucrose-induced increase in thermogenesis, and we do not draw any conclusions from that. So, in line with these findings, we can draw a clear conclusion. Our hypothesis is correct, although our calculations were a bit more in-depth. Despite the fact that participants in baseline measures differ, we saw clear differences in reaction after taking the intervention in the form of sucrose or in the form of water. P1 had a higher RQ due to carbohydrate oxidation. P2 remained pretty much the same. The reason we did not include energy expenditure is that there were no significant differences, and this would not lead to a certain conclusion. Now we would like to thank you for watching. Bye.